Hello, I'm Vijit. My student ID is S3799493, and this is my individual presentation for the IDM project. For this project, I worked in a team of 3 along with Arlo and Joshua. I'll start by giving a brief overview of our approach. We worked on automated music generation, but let's talk about some of the research that's already been done using ASP in the domain of music generation. In a recently, researchers have attempted to generate music using attempted to generate music using ASP. Some examples include 12-bar blues. A system called Armin can also generate a trance music. Furthermore, another system called Anton can generate classical music, which was developed by the researchers at University of Bath. In our approach, we implemented ASP to generate different genres of music, such as lo-fi jazz, house mix, and classical music by using a set of notes and chords as atoms in the output models with the help of choice rules, integrity constraints, and optimization techniques provided by the ASP language. So the purpose of experiment 1 was to compose music in the style of lo-fi jazz house mix. This kind of genre is generally is usually found on YouTube study playlists. Low fidelity generally is considered a music where the sounds are considered imperfections in the context of production quality. This kind of sound is usually played through an old or poor quality speaker. The jazz house part is essentially a cross between two genres, where the jazz part is used in our implementation. We use the jazz part by including 7th, 9th, 11th, and 12th chords, and the house part comprised of the repetitive rhythmic structure in our implementation. The logic program written for this experiment was input as a string to Klingo API using Python. The information database for the logic program consisted of notes and chords defined in E-Dorian scale, along with a set of drums, basic set of drums. To define chords in a sequence, we used steps predicate that was defined from 1 through 8. For defining different instruments, we used a predicate called grid, which was defined in 4 by 8 2D structure. The first assign choice rule that was implemented was to assign the root chords as the first chord in the sequence, which usually governs the center point of the chord progression. The second choice rule we assigned was used to assign the chord in every step afterwards. The third rule was used to assign a note to every position using grid predicate, and the last rule containing beat was used to assign the drums. After this, we implemented a list of integrity constraints. First one was used to ensure that the same note was not assigned twice in a row. The second one was used to make sure that a clash did not occur between notes at the same time. Furthermore, next set of integrity constraints were used to make sure the same chord is not played twice, and also the same root chord is not played sequentially. In optimization, we minimize the frequency of false notes that occurs in the note progression to make the sound continuous. We also maximize the output of note assignments that were root, third, fifth, or seventh. For our output, a random model was picked, parsed using basic Python functions, and stored as note strings. We used multiprocessing to play the output. The multiprocessing system we used to play the file worked out of time at sometimes and did not sound good. Therefore, in the next experiment, we ended up using MIDI output. Let's hear this file and see how the output, check out some of the results. Let's move on to experiment 2. The purpose of experiment 2 was to generate classical music. This was a slightly more complex problem. So, in the field of music generation, the information database is generally composed of notes and chords with different pitches and duration. A note is a building block of much of the music that's written. In Western music, there are 12 musical notes, namely C, C sharp, D, D sharp. As you can see on the screen, it goes all the way to B. So in piano, there are a total of 88 notes. However, when all 12 notes are played, it is considered one octave, and after the same set, 12 notes are repeated, the higher or lower octave. We used 35 chromatic notes in our program. Let's talk about chords. Chord, on the other hand, is a combination of 3 or more notes, depending on the type of chord it is. In our implementation, we focused on triads, meaning a combination of 3 notes where the first note is called the root note that gives the name of the chord, while the other 2 notes decide the type of chord it is. Usually in our case we implemented major, minor, suspended 4 and dominant 7 chords in this implementation of experiment 2. So to create a whole song, we defined a 16 by 16 grid where one chord was assigned to every step on the first axis and 16 notes were assigned on the y-axis. The melody was chosen to be notes contained within a scale of the chord that was currently being played. For instance, if we are playing E major chord at a certain step, the melody would be selected from the predicate of notes contained within the A major scale. This pattern was repeated for all 12 notes combined with 4 model scales. To play notes in a lower and higher octaves, we also added a rule for scale predicate to keep this in mind. So in case of integrity constraints, the first set of integrity constraints that you see on the screen were used to make sure that no same note is played twice in a row. The second the second set of constraints that we used were to prevent the chords from repeating. The third constraint that we used ensures that if dominant 7 chord is assigned to a bar, then the next bar will be a root. Now, the output generated from this experiment 2, from the experiment 2 ASP, was parsed into a list of notes and chords. In this next step, we implemented a class that combined the two lists into a single 2D NumPy array. This was implemented using a sequence of 15 notes in a row followed by a chord throughout the entire musical piece. Each row of the NumPy array has 88 columns and the index of each column represents the corresponding piano note, with the value at each index representing the velocity at which that note should be played. Furthermore, each row in the NumPy array represents the note or a chord that should be played at a given timestamp. After the NumPy array conversion, subsequently the array is in our implementation, we converted the array into a MIDI file. To convert a NumPy array into a MIDI file, we used a Python package called Mido. The contents of a MIDI file usually have a list of messages that contain the information of what to play next, along with the other parameters such as track details, key signature, instrument details, etc. There are two kinds of messages in a MIDI file, as you can see on this image in the screen, namely a meta message and a regular message. In the meta message, we define the tempo, use the set tempo parameter that specifies the number of microseconds in a beat with a value of 500,000, which generally controls the pace of the musical piece. In the message, we defined the channel for the piano instrument and then used a list of parameters such as note on, note off, note, velocity, and time. In this image is a sample of chord sequence that contains the information about 3 notes, namely 50, 53, and 60, which are part of in this instance, which are part of the chord. Along with the intent, so in this implementation, we along with the intent, we are using the name of the three notes along with the intensity at which this note should be played using the velocity parameter. The note on and note off parameter indicates the information about when to press and release the note respectively. Excuse me. So the final output of our result with converted MIDI came out to be sounded more like a Pokemon music battle. Although this was unexpected, later we realized that in the MIDI conversion process, we could tweak around some more MIDI parameters and such as velocity, time, note on and note off to create a better sounding music. So without further ado, let's just check how our music sounds. So as you can see, this was the output from experiment 2. So in conclusion, I would like to say our aim was to check the potential of ASP in the domain of music generation. Although we were able to create precise control over the output using optimization statements, we believe ASP has potential to generate interesting musical pieces that are free from human bias and not explicitly programmed. Thank you.